Hello, everyone. This is the problem video for 7.4. And I'm going to mostly pull these from the textbook. I'll try and take a look at the web assigned homework at the end. Okay. So first of all, let's deal with this situation. This is number 7 in the textbook. When we're doing partial fractions, okay, so let's say we're integrating this. The first thing we need to do is make sure the degree of the top, the numerator, is smaller than the degree of the bottom. So we don't have that in this case, right? The degree of the top is 4, degree of the bottom is 1. So how do we deal with that? Okay, if degree of top is greater than or equal to degree of bottom, first thing we do is polynomial long division. So I need to divide x to the 4th by this x minus 1. Okay. So I'm going to fill in the rest. Since I only have x to the 4th, I'm going to go ahead and fill in all the rest. Okay. And then I'll do my polynomial long division. Okay. So polynomial long division is all about matching the first term. Okay. So I want to match this x to this x 4th. So what do I need to multiply x by to make it x to the 4th? I'll multiply by x cubed, right? So I'm going to put an x cubed up here, and I'm going to keep everything in line just to make it neat. So I'm going to put my x cubed above the 0x cubed there. Okay. And then, all right, I figured out what I need to multiply x by to get x 4th. And now I'm just going to multiply this entire thing by x cubed. And when I do that, I get this, right? X to the 4th minus x cubed. And then I'm subtracting. I'm going to put this whole thing in parentheses and subtract it from what's above. I put this in parentheses to remember to distribute the negative, okay? That's a big source of errors, okay? So let's see. When I do x to the 4th minus x to the 4th, those cancel out completely, right? So there's nothing in this space. And then I have, what do I have? I have 0 minus negative x cubed. So I add x cubed, right? So I end up with positive x cubed. And then I just bring down the next term, okay? I don't really have anything else to bring down, but I'll put 0x squared, bring that 0 down. And then I repeat my matching process. I want to get this term out front, this x to match, I want to get this term to match this term. Okay, so what do I need to multiply x by to match x cubed? I need to multiply by x squared. So I want to put plus x squared here. Okay, I multiply x squared by this, and I should end up with x cubed minus x squared. And then again, I put that in parentheses and then do my subtraction. And I end up with x squared. Then I bring down my 0x. All right. Repeat my process. Bring down my 0. Okay. And now once I'm at this stage, I have a 1. There's no, I shouldn't use, let's see, I'll say that I want this stuff up here to just be a polynomial, right? So if I try and get this, this x here to match this 1, I would have to multiply by like 1 over x, right? So I don't want to do that. So that's my signal to stop, okay? And usually when I have a constant or something like that, I stop. And what's going to happen with this leftover stuff? That's going to be my remainder. Okay. So my answer would be, after I do polynomial long division, I'm going to have all this stuff on top of my division sign, right? Plus that remainder. What remainder did I have? 1. And then I'm going to put the remainder over what I divided by originally. Okay. So when I do my polynomial long division, I end up with what, x cubed plus x squared plus x plus 1 plus 1 over x minus 1, right? So that's what I get when I do x to the 4th divided by x minus 1. Okay, I end up with this thing. Okay, so now what does my integral become? Instead of having x to the 4th over x minus 1, I have x cubed plus x squared plus x plus 1 plus 1 over x minus 1 dx. And now I can integrate all of this stuff, right? I don't even have to do partial fractions. Okay. So this is my antiderivative. In other problems, maybe this term here will still require partial fractions, like breaking that up using partial fractions. So that would be the next step in those cases. Okay, but this is a good problem to just show polynomial long division. All right, moving on. Let's try number 9, and I'll try and go a bit faster. Actually, let's not even do number 9. Number 9 is a bit easy because they give us the bottom in factored form. Let's try number 11. But let's see, they give us a definite integral, but I'm going to make it an indefinite integral just to save a little time and review. Okay, so let's see. I get 2 over 2x cubed plus 3x plus 1. My first step would be to factor the denominator, right? So let's ignore the integral sign for a second, and let's just think about the fraction, and let's try and factor that denominator as much as possible. How can we factor that? Well, first thing to notice is I've actually written down the problem wrong, so it makes it a lot easier if I write it down correctly. It's 2x squared plus 3x plus 1. Okay, so this is now a bit easier to factor. We could try factoring, or we could plug in one strategy I use sometimes is if this doesn't look easy to factor, but I can like plug something in to the denominator and get 0, that tells me it's a factor, right? So let's say I plug in -1 to my denominator. What do I get? I get 2 minus 3 plus 1 is 0. Okay, so I know, let's see, x equals -1 is a root. So that would be, writing that would be x plus 1 is a factor of this thing. Okay. So how do I find the other factors? Well, at this stage I could do polynomial long division. Okay. So I could do 2x squared plus 3x plus 1 divide by x plus 1. And this is going to divide out, and it's going to divide out cleanly and give me a polynomial. So there's not going to be any remainder. Okay. So let's see. Dividing this, I would have 2x. Okay. Oh, it looks like a repeated root. Oh, maybe not. Let's see, 2x plus 1. And then I get a remainder of 0. Okay. So when I divide this by x plus 1, I get 2x plus 1, which means my other root is 2x plus 1. Okay. So my fraction, the denominator factors neatly as x plus 1 and 2x plus 1. Okay. And maybe you're good at factoring. I don't ever do the factoring by thinking about the coefficients, things like that. I just do it like this. If you can do it the other way, that's fine, as long as you end up with this. And then by partial fractions, let's see, I got two distinct linear terms, so I know that's going to split apart as this. A over x plus 1 plus b over 2x plus 1. Okay, so let's write that. And now it's just about finding those constants. So I multiply everything. I multiply both sides by that denominator. And after canceling, I should have that. And then I could use one of my methods to figure out what these constants are. So let's say I wanted to use the method where I plug in stuff to these to get some cancellations. Okay. What could I plug in? I could plug in x equals -1. On the left side, I would have just 2, since the left side is constant. On the right side, I'd have a times -1, and then plus 0, because that term would cancel. So let's see, a equals -1/2. Okay. What could I plug in to get cancellation here? -1/2. So do x equals -1/2. When I do that, on the left side I get 2. On the right side, the a is going to cancel. This term is going to be, first term is going to be 0, and then I would have b times +1/2. So let's see, 4 should equal b. So I know what my constants are. Okay, so I know that 2 over x squared plus, 2x squared plus 3x plus 1 equals -1/2 over x plus 1 plus 4 over 2x plus 1. Okay. So if I want to integrate this, I could instead integrate the right side. Okay, so let's integrate the right side now. What is this integral? I'll do it mentally and let you guys figure that out on your own. Let's see, it would be -1/2 ln x plus 1, and then plus what? 2 ln x plus 1. Excuse me. 2x plus 1 here plus c. So that should be our antiderivative. Again, this problem asks for a definite integral, so you would just plug in the bounds at that point, but I'll skip that step. Let's try number 19. Again, they give a definite integral. I'm not gonna do the bounds. I'm just gonna make it an indefinite integral. Okay, so let's say I have x squared plus x plus 1 over x plus 1 squared times x plus 2. So first thing, is the degree of the top smaller than the degree of the bottom? Yes, because if I multiplied all this stuff out, let's say I would have an x cubed term on the bottom plus a bunch of other junk, right? If I multiplied all this stuff out. And then on top, I just have x squared. So yeah, degree of bottom is bigger than degree of top, so I don't need to worry about polynomial long division. I can just skip straight to my partial fractions. And this problem is nice because it gives us the bottom already factored, right? So I don't need to factor the bottom. So now I just go straight to the problem of deciding which case this is. So let's consider this fraction here. I have x plus 1, that's a linear term, but it's squared. Okay, so I have repeated linear terms. So remember how that works. Let's see, I could get rid of this x plus 2 first. I could do like a over x plus 2 if I wanted. And then I could do, well, I would do b over x plus 1. And then remember how I deal with the linear term, a repeated linear term, I would do c over x plus 1 squared. Okay, so that's my setup for this. Now, the rest is the same, okay, as any case. So I multiply both sides of my fraction by, both sides of my equation by this denominator here. When I do that, on the right side, or excuse me, on the left side, I'll just have x squared plus x plus 1. On the right side, what would I have? A times x plus 1 times x, no, x plus 1 squared, right? Okay. Then I'd have b times x plus 1 times x plus 2, and then c times x plus 2. All right. Now at this step, you could try, if you prefer the method where you plug stuff in, that's fine. It shouldn't work. It shouldn't give you all three constants though, if my intuition is correct. This repeated linear factor is going to throw a wrench in that if you just like plugging stuff in. Let's try it though. Okay, so let's see. Let's see what can we plug in to get this a to cancel and this b to cancel. Well, if I plug in x equals -1, then let's see, this will cancel because I'll have multiplied by 0 here and here, and then this should be left. Okay. So on the right side, I would have c times -1 plus 2, which is 1. What would I have on the left side? Plugging in -1 to here, I would have 1. So we see 1 equals c times 1, so c equals 1. Now what can I plug in? Well, there's only one other thing to plug in, right? -2, okay? Because I've plugged in -1. The only two roots I have are really, I have x plus 1 and then x plus 2, right? And then on this term I have both. Okay, so that's all I have to work with. So I could plug in x equals -2 to get some cancellations, and let's see where that takes us. On the right side, let's see, I would have a times -1 squared. So a times -1, and then the -1 is squared. What would I have here? I'd have multiplied by 0 here, so that's going to cancel completely. And then this is going to cancel completely as well. So on the right side, I just have a times -1 squared. In other words, a times 1. What do I have on the left side? I plug in -2. Let's see, I get 4 minus 2 plus 1. So I get 3. Okay. So I get a equals 3. Now the problem is I still got to figure out what c is, and I don't have anything that's going to give me nice cancellations anymore, right? But there's a way around that where this equality holds for all x, meaning I can actually plug in any x here, It's just that when I plug in like -1 or -2, that gives me nice cancellations. But I've kind of run out of x's that will give me nice cancellations. So what can I do? I can just plug in any other value of x and then plug in what I know for a and c. I know what a and c are, right? And then that should hopefully be enough to find b. So let's try that. So what is a convenient value? 0 is always a convenient value to use, right? So I plug in 0 on the left side, and what do I get? I get 1. And then on the right side, what do I get? I know a is equal to 3. So I get 3 times 1 squared, so 3 times 1. I don't know what b is, so I get b times 1 times 2. And then I know c is equal to 1. And then I'm plugging in 0, so I get this. All right, so I get 1 equals 3 plus 2b plus 2. Okay, now it's just solving for b. So if I have this equation, let's see, I would have -2, -4 equals 2b, so b equals -2. Okay, now let's just plug our constants into this. So my original integral, my integrand, this stuff, is going to equal this. So I'm going to plug in a, b, and c. So let's see, I have 3 over x plus 2 minus 2 over x plus 1. Yep. And then plus 1, x plus 1 squared. Okay. So my original integral is transformed into this integral. And now it's just a matter of integrating. So when I integrate each of these, let's see, first one would be 3 ln of x plus 2, right? Second one would be minus 2 ln x plus 1. And then what is this last integral? Well, we can solve that with a u sub, but let u equal x plus 1. And then I'll have that integral become 1 over u squared. So it should be -1 over x plus 1. You guys can try that on your own to see why that works. Let me know if I did it wrong, as always. So I should have this antiderivative. And then, like I said, if it's, if you want to do the definite integral and check your answer in the back of the book, just plug in the bounds to this antiderivative. All right, so we've seen a case 1 and a case 2 so far. This previous problem was a case 2. Let's check out case 3 and case 4. So let's say I have number 23. Okay. So let's say I have the integral 10 over x minus 1, x squared plus 9. Okay, so again, they give it to us in nice factored form. Great. So right away, I see I have a irreducible quadratic, right? X squared plus 9, I can't factor that anymore. So I know I have case 3. So I know when I split up my fraction, when I apply partial fractions, it's going to become this. A over x minus 1 plus bx plus c over x squared plus 9. And again, if you guys are doing things in a different order, that's fine. Okay, so order doesn't really matter. So you could have also split it up as, ax plus b over x squared plus 9 plus c over x minus 1. That is also acceptable. So don't be freaked out if you're doing things in a slightly different order than me. I will continue using this one. Okay. So next step, to multiply both sides by this denominator. On the left side, I'm just left with 10. On the right side, I'm left with a x squared plus 9 plus bx plus c, put that in parentheses, times x minus 1. Okay, so remember, you've got to distribute, you got to multiply this entire term, bx plus c, by x minus 1. Okay. Now I'm gonna, so we've used the plugging in method where I plug in values. That's definitely not gonna work for this. There's nothing I can plug in to x squared plus 9 to get 0 here. So this is this term a times x squared plus 9. That's never going to cancel out. Okay. Maybe I could work around that with some clever choices of things to plug in for x, but I'm not going to. And for this problem, I'm gonna switch to doing the system of equations method. So how does that work? Okay, and this is actually what I wouldn't say I prefer. I switch pretty freely back and forth between the two methods. So I think that's probably best if you have that ability. But that's neither here nor there. So how does this work? I'm going to multiply everything out on the right side. So I'm going to actually multiply all these terms out. Okay. So the first one becomes ax squared plus 9a, right? And then what does this one become? Let's see, bx squared minus bx plus cx minus c, okay? And then I'm just going to regroup all my terms so I get like all the x squareds together, all the x's together, and all the constants together. So let's see, I have ax squared and plus bx squared. So I'll write that as a plus b times x squared. Okay, boom. Those are taken care of. Now I got minus bx plus cx. So I'll write that as, I'll write that as negative b plus c times x. Okay. And then I got constants 9a minus c. Okay. And now it's a matching game, right? I look at the left side and I look at the right side. There's no x squareds on the left side. So I know that a plus b has to equal 0. Okay. Again, now I look at the x term. There's no x's on the left side, so I know that negative b plus c equals 0 as well. And now I come to the constants. I have a 10 on the left side, all right? And then I have 9a minus c on the right side. So I know 9a minus c equals 10. And notice how I've written everything in nice lines where all the a's are in the same column, all the b's are in the same column, all the c's are in the same column. That's going to make this system of equations method just a bit easier. Okay. All right. So now I want to start solving for my constants. Okay. So this would require a couple steps because there's no one equation or no set of two equations that's going to give me a nice cancellation. So I'll show you how I would do this. First, I'm going to add the first two equations together. All right. When I do that, I'm just going to add them vertically. Okay. So I'll write them down here again. Okay. When I do that, when I add them vertically, I get a plus nothing is a, b plus negative b cancels out, and then I got a c plus nothing is c. So a plus c equals 0. Okay. Now let's combine that with this equation here. I should be able to get a value of something. I know 9a minus c equals 10. So now let's add these two equations together, again vertically. So I get 10a, the c's cancel out, and I get 10. So a equals 1, right? If 10a equals 10, then a has to equal 1. Now that I know a equals 1, okay, let's look at this equation that's dangling right here. A plus c equals 0. If a equals 1, then that means c has to equal -1. Okay, so now I know what a and c are. And now let's look at our kind of bank of equations again. Let's look at this thing. I know what a and c are, kind of solve for b. Yeah, so I know what a is, okay. I can figure out what b is from this first equation. Okay, so if a is 1, then b has to equal -1 as well. All right. So now, let's see where, so I can now plug my a, b, and c into this thing. Okay. So I had 10 over, so x plus 1 squared, no, x plus 1, x minus 1. So my original thing is going to equal a over x minus 1. I now know that a is 1. So 1 over x minus 1 plus bx plus c over x squared plus 9. Okay, so let's see. This b should be -1, and this c should be -1 as well. Okay. Now, so this left side equals this right side, so I could integrate this thing. All right. One thing that might make things easier, right now I have it like this: 1 over x minus 1 plus -1x minus 1 over x squared plus 9. I'm going to factor out a -1 here, right? So this is the same thing as this. And then I'm just going to change this plus sign to a minus sign. These are equivalent. Okay. So now maybe it's a bit nicer to look at now. Okay. I'm going to integrate this thing. Okay. This part, that's easy to integrate, right? That's just one of those ln times integral. How do I integrate this thing on the right side? Well, I need to split it up. I need to split up that fraction right down the middle. Now here's something you got to be careful about. Okay, let's put this in parentheses for now. Think about this fraction in parentheses. Okay, so split it up in parentheses first. Okay, when we split up the stuff in parentheses, it becomes +1 over x squared plus 9, right? And then this negative is distributed to both of these. It's an easy mistake to make, so keep an eye out for that. All right. Now, as I said, this first thing is just it's an easy integral. It's ln x minus 1. Now, what's the second one? Okay, integrating this, that would be what? 1/2 ln x squared plus 9. Okay, if we did like a u substitution, u equals x squared plus 9, you would see that. And then what's the third integral? What is this thing? That's going to be one of these tan inverse types of integrals. Let's see, so let's focus on this thing. Okay, and this is one of the ones where I can't just do it in my head. I think it would end up being 1/3 tan inverse x over 3, something like that. But it's not something I have right at the tip of my tongue or tip of my fingers, whatever you want to say. So I'm going to write that down here. X squared plus 9. Okay. I'm going to integrate this. So to get this into a nice tan inverse type integral, I need to factor out this 9, right? So let's see, let's pull out that 9. then I would have x squared over 9 plus 1. And then this x squared over 9, I can consider that as x over 3 squared plus 1. Okay, I pull out the 1 over 9 from the integral. I do a u substitution. U equals x over 3. And then 3 du equals dx. Okay, and then I pull out that 3. Now I see it's a nice tan inverse u times 1 over 3. I undo my substitution. Okay, so yeah, 1/3 tan inverse x over 3. So that means this stuff becomes minus 1/3 tan inverse x over 3. And I got my plus c. So this would be my final answer. Okay, so that is our type 3 partial fraction. So let's trudge through one more and let's do a type 4. So type 4 is going to be repeated irreducible terms, right? So let's find one of those. Looks like number 35 is one of these. Okay, so number 35 from the book. It also looks like it's going to be a long one. So we got this. Okay. So we're trying to integrate this thing. 5x to the 4th plus 7x squared plus x minus 2. Excuse me, plus x plus 2. Divided by x times x squared plus 1 squared. Okay, so first check degree of bottom's bigger. Let's see if I multiplied all this out. Okay, x squared squared, that would give me an x to the 4th plus blah, blah, blah. And then times x, I would have x to the 5th plus blah, blah, blah. Okay, so degree of bottom is 5. Oops, make a mess of everything. So degree of bottom is 5. Degree of top is 4, so we're good. Okay, and they already give it to us in factored form, right? This denominator is factored. The problem is we have a repeated term here, and this repeated term is irreducible, right? So I have the case where I have repeated irreducible factors. Okay, so I know when I set this up, I'm gonna have 5x to the 4th plus 7x squared plus x plus 2 over my terms here. I know that's going to be a over x, so I got a for over x for this. And then let's see, I got my bx plus c over x squared plus 1. And then what would I have? Dx plus e over x squared plus 1 squared. So this is the setup for case 4. All right, now, next step. All right, so now I need to solve for my constants. Now, again, this is a case where maybe the plugging in method won't work, or it won't work for to find all our constants, but we could try it. So let's see. First, I would need to multiply both sides by my denominator on the left side, right? Correct. So I end up with a times x squared plus 1 squared plus bx plus c times x squared plus 1 times x, and then plus dx plus e times x. Okay. Now, is there anything I can plug in to get some nice cancellations? Well, no matter what I plug into here, one's going to cancel. Well, let's see, if I plug in 0 for x, since I'm multiplying by x here and here, those terms will cancel. Okay, so let's see what happens when I plug in x equals 0. on the left side, I am just left with 2. On the right side, I would have a times 0 squared plus 1 squared, so a times 1 squared. Then everything else cancels on the right side. So in other words, I have a equals 2. Okay. Unfortunately, since this is irreducible and this is irreducible, and I've already plugged in x, right? So nothing else I can plug in is going to give me cancellations for here and here, here and here. So this is kind of an indication maybe I need to switch to system of equations now. So unfortunately, what I got to do is just multiply this right side out completely. So let's say on the left side, I still have my 5x to the 4th plus 7x squared plus x plus 2. On the right side, let's go ahead and multiply everything out. I have a x to the 4th times 2x squared plus 1. Doing this in steps. Then I would have bx plus c times x cubed plus x. Then dx plus e. Well, I could just go ahead and write that as dx squared plus ex. Okay. I actually have done this already. I had to do a second take because my internet cut out. Okay. So here, let's see, on the right, left side, I have this. Okay, on the right side, I have this. And then I still need to multiply this a to everything, and I need to multiply all this out. Okay. And when I do, I'll kind of go ahead and skip down conveniently because I've kind of already blocked everything out. When I do that, I should be left with this. So, once I multiply everything out, I'll be left with this. I'll erase everything. Okay, so once I multiply everything out, I'm left with this stuff. So let's just kind of condense everything. Okay. So I go from here to here. Now it's playing the matching game, right? So I need to match the coefficients on the left side, meaning I need to match the coefficients here to the coefficients in here. Okay. So let's see. Let me just erase this. It's no longer relevant. Okay. So I'll refer to this. I'll refer to this stuff as the left side and all of this stuff to the right side. All right. So on the left side, I have 5x to the 4th, right? And then on the right side, let's see, what do I have? ax to the 4th, bx to the 4th. So I know that a plus b has to equal 5. Okay. Now let's consider x cubes. Do I have any x cubes on the left side? No, I don't. But on the right side, let's see, I have cx cubed. So that tells me that c has to equal 0. Now let's move on to x squareds. On the left side, I have 7x squared. Okay. Let's just kind of eliminate these things as we account for them. Okay. So on the left side, I have 7x squared. On the right side, I got 2ax squared, bx squared, dx squared. So 2a plus b plus d has to equal 7. On the left side, I have a single x. On the right side, I have cx plus ex. So c plus e has to equal 1. Let's clean this up a bit while we go. Okay. And then finally, our constants. On the left side, I got 2. On the right side, I got a, and we already know a equals 2, right? Okay. So now it's just about solving this system of equations. So let's keep track of what I know. We already know a equals 0, or excuse me, a equals 2, and then we know c equals 0, right? Okay. Now that I know c equals 0, I can solve this thing. Okay. So e has to equal 1. Okay. Now I know a, c, and e. Since I know a, I can solve for b in here, right? So b has to equal 3. Now all I need is d. Okay. Let's see. So let's look at this equation. I know a is 2, so I have 4 here. I know b is 3. So I got 4 plus 3 plus d equals 7. So d equals 0. So these are my constants. All right. Now let's plug those in to here. Okay, so let me copy this. Bring it down. All right. So what do we know about a? A is equal to 2. What's b? B is equal to 3. C is equal to 0. D is equal to 0. E is equal to 1. So I should have this. Now I can integrate. So if I want to integrate this left side, I instead integrate this right side. And those integrals are 2 ln of x plus, let's see, 3 over 2 ln x squared plus 1 plus, what is this integral? This would be, this is actually this looks like a trig substitution integral, actually. So this is something, since this problem is kind of late in the textbook, it's harder difficulty. Or, since it's kind of a higher number of problem, it's more difficult. So this is, I would say, is maybe a bit more difficult than you might see on the test. But let's try it. 1 over x squared plus 1. If I want to integrate this thing just by itself, let's see, this looks like a tan substitution. So let's try it and see what happens. So we get secant squared theta tan squared plus 1 squared dx. So we get secant squared over secant to the 4th. So 1 over secant squared, which is cosine squared. Okay, so, and then cosine squared we turn into 1/2, 1 plus cosine 2 theta, 1/2, and then let's see, so we get 1/2, the integral is 1/2 theta plus sine 2 theta over 4. And we turn that 1/2 theta, okay, to, that becomes sine 2 theta, no, sine theta cosine theta over 2. And then triangle. Let's see. This is so I should get this for my integral of, oh wait, no. Yeah, I think that should be right. So that should be my integral of that one piece. Okay, so let's plug that in up here. So I should be left with this. And then, of course, I need my plus c. And I just looked in the back of the book, and it is correct. That one's a bit much, but hopefully you guys see how the system of equations is done. It wasn't actually that bad, right? The system of equations wasn't that bad. And, you know, the important part is the setup of case 4. So don't worry too much. There isn't going to be one this difficult on the test, but if you can do this one, great. I think you're in good shape. All right, so I'll end this problem video there.